Okay, so in this video, we're going to look at the second chi-square test, that is testing for independence of two variables. So suppose we had over here a random sample of 100 observations. So here, in fact, these observations are clients at a bank. And so we see that we've got here two variables, two different variables, fund type and level of satisfaction. And each of these variables provides information about the client. So we have 100 rows of these two variables. And one better way to organize this data is to create a cross-classification table, or otherwise known as a contingency table, whereby here, we look at the number of categories for fund type. In this case, there are three: bond, stock, and tax deferral. And we look at the number of classifications or categories for level of satisfaction. In this case, it would be high, medium, and low. So if we create a contingency table to summarize these, um, the frequency count for these two variables, we get we get something over here that looks like this. In fact, this is actually the same example, the same random sample of 100 customers. And here we have created a contingency table. So on the vertical over here, we've got the fund type. And here across on the horizontal, we've got the level of satisfaction. Okay, so now what we want to do through a chi-square test is to determine if these two variables are in fact independent or not. So let's go back over here. The idea is that we will be again comparing the actual observed frequencies in each cell found in each of the cells in the contingency table versus the expected frequency count that should be appearing in each cell. Now, going back once again to that contingency table right here, I see that if I am crossing two variables whereby the first variable fund type has three categories and the second variable level of satisfaction also has three categories, then that should give me over here 9 cells, right? So I should have 9 observed frequency counts. And corresponding to these frequency counts, I should have expected frequency counts. So 9 expected frequency counts. Let's go back to how to look at the way these cells are identified. So cell Fij, this represents the frequency count for uh, a fund, a bond type I, and level of satisfaction J. So in other words, say F12 would mean that I'm looking here at the frequency count for customers who have a fund type. Let's just go back over here. A fund type, a bond, that would be the first type of the first category in fund type, and the level of satisfaction here would be the second level of satisfaction, so medium. So in fact, I would be looking at cell 1, 2, which would be this one right here. This gives me the actual observed frequency count here. So I've got 12 customers who happen to have a fund type that is a bond and a medium level of satisfaction on their investments. 12 customers. That is for the observed frequency count. Now, right below is the counterpart. This is the expected frequency counts for the corresponding cells. So how do I compute expected values over here in each cell? Let's go back to that slide once again. The expected frequency count is represented over here by E with a, notice a hat, subscript ij. In other words, E hat 1, 2 would have a value over here, which is equal to my total for row I. That would be my total for a bond type of fund times the column total for medium level of satisfaction. And so that would be divided by n, my sample size. Now, just to discuss a little bit the notation over here, we put a hat on expected value simply because the data that we are using over here is coming from our sample. Our sample that is randomly selected of 100 observations. Hence, this is a sample expected value. Okay, now this formula over here that we have is simply coming from the format that would be n times pi times pj. So pi being the probability of the first variable and pj being the probability of the second variable, right? Okay, and so when you cross out the ends, you are left with this formula right here. Okay, so the proper format over here, if we are going to conduct a hypothesis test, is to write out first the null hypothesis. In this case, we are looking at the statement in the null hypothesis. We say that the two variables or the two classifications are statistically independent, and the alternative says something somewhat opposite. It says that the two classifications are not independent, are statistically not independent or dependent, if you wish. And this null hypothesis will be tested out at a specified level of significance alpha. So alpha again can be 0.05, 0.01, or 0.10. Depends on what on what you're interested in using over here. We will also need a test statistic. The test statistic will, of course, measure the difference between the observed frequency count and the expected frequency count. The larger the difference between the two, the greater the test statistic chi-square will be, right? So this difference is, of course, squared, and it is divided by the respective E of ij. Okay. Again, the decision rule is the same, whereby here we will reject the null hypothesis if and only if the test statistic happens to be greater than the critical chi-squared at a specified level of significance alpha for a number of degrees of freedom, which I will discuss just after. This is, of course, using the critical value rule. Should you use the p-value rule, then the idea over here is that you want a p-value for your chi-square test statistic that is less than the level of significance alpha. This p-value, of course, is determined for the specified degrees of freedom over here. So how do we calculate degrees of freedom in this type of hypothesis testing? Well, here we look at degrees of freedom is the product of number of rows you have. In other words, the number of categories you have for variable 1. So that would be number of rows minus 1 In this case, we said that we had, in fact, we have 3 categories for variable 1. So I've got, in fact, 3 rows, hence 3 minus 1 would be the, the first part that would go in this product here. So that would be 2, and you multiply that by the number of categories that you've got in your second variable minus 1. So that's number of columns minus 1. Looking again at my contingency table, I see that for my second variable here, I've got 3 categories. That's 3 columns minus 1 gives me 2. And so here I've got 2 times 2 degrees of freedom. Okay. Um, okay, so let's just continue over here. So here we can see how we would get an expected value for cell 1, 1. That would be the result of taking here my row total for row 1 times my column total for column 1. So 30 times 40, and that would be divided by 100 would give me 12. And you repeat that for every other cell, every other of the remaining 8 cells to get your 9 expected values overall. Okay, so here we are where we see how this test statistic is actually computed. And so essentially here we can see how when we take the chi-square values for each cell, right? So in this case, I've got 9 cells. So this expression would be repeated 9 times, and I would sum them up. So for example, the first chi-square value that I get over here would be the actual observed value in cell 1, 1. Let's go take a look and see what that value is. That would be actually 15. And I would compare that to the expected value for cell 1, 1. That would be 12. And so here I would square the difference and divide it by 12. Okay, until I get to my last cell over here, that would be my 9th cell. So here I would be comparing my cell 3, 3, the observed frequency count minus the expected frequency count for cell 3, 3 squared and divided by 8. That would be the expected value for cell 3, 3. So this gives me a chi-square of 46.4375. The idea over here is that if I'm going to use the critical value rule, then I want to make sure that my critical value will indeed be that the test statistic chi-square will be greater than the critical value. Now I just want to go through an example over here. So here we are. So here we have an example where we've got whether uh, the person is a smoker, and if so, what is the level of smoking? So so here we've got the first variable being smoker, and we've got 3 possible categories over here. We've got the value heavy, moderate, and non-smoker. These are the 3 possible categories for the variable smoker. Then we've got a second variable on the job accident. And so here we've got 2 categories of answers. We've got yes and no. And so this information is taken over a random sample of 66 employees. Okay, so by classifying our information by category and crossing the two variables, we get this contingency table right here. So I know, for instance, that here I've got 12 um, employees are heavy smokers and had an on-the-job accident. Okay. The idea is that now I will compare these observed frequency counts to expected frequency counts. The expected frequency counts will be determined by applying the formula that we saw just before. Here we are. This is the formula right here to determine the expected frequency count for each cell. Now, if I go back to that example once again, I see that in fact, here I've got uh, 3 categories for variable 1 crossed with 2 variables for variable 2. And so that gives me 6 cells. I've got 6 cells. So I will be calculating 6 expected values. Here are the expected values right here. So an actual observed count of 12 for category 1 of variable 1 crossed with category 1 of variable 2 versus an expected value of 8.24. Now by applying the formula right here, this formula right here, I am able to get my test statistic chi-square. Let's go back and see what that statistic actually is. So here we are. I get here my test statistic right here. Okay. Let's just check here. I've reproduced here the same information, exactly the same information in Excel. And so here I have my test statistic is a 6.86. This is by applying the test statistic chi-square formula. And here I've got my critical value chi-square. Now, if I go to the problem over here, it's asking me to test whether the two variables in question are independent or not. And this should be tested at a level of significance here that is specified to be at 0.01. So at 0.01, my chi-square value, at 0.01, my chi-square value is in fact over here equal to 9.21034. This is for 2 degrees of freedom. How do I get this 2 degrees of freedom? Let's go back to the slide and see once again. 2 degrees of freedom is as a result of taking the product of number of rows minus 1. Here I've got 3 rows minus 1 is 2, times number of columns minus 1. I've got 2 columns minus 1 is 1. So 2 times 1 gives me 2 degrees of freedom. And so I get over here my corresponding critical value, which you can get, by the way, directly in Excel by clicking on the formulas, going into your functions, statistical functions, and over here, I'm going to look for the, I'm going to look for the chi-square inverse right value. So in other words, this is giving me the corresponding critical chi-square value for a right tail area of 0.01 and for 2 degrees of freedom. Okay. Now, with these two values identified, I can now make a decision The decision rule being that if my test statistic is greater than my critical chi-square, then I can reject the null hypothesis. Over here, my test statistic of 6.86 is not greater than my critical chi-square of 9.21. Hence, I do not reject the null hypothesis. If I were to use the p-value approach, the idea would be to compare my p-value for my test statistic of 6.86 and for 2 degrees of freedom, assuming that the null hypothesis is true. It would have to be compared to my level of significance. The level of significance for this example is 0.01. So 0.03 is in fact not less than the level of significance of 0.01. And hence, again, I do not reject the null hypothesis. Once again, very quickly, I want to show you the decision rules stated right here, right? So we see the decision rules are stated right here, and that is how we come up with the same conclusion, regardless of the approach that I'm using. So that is pretty much all for um, the chi-square test, the chi-square test to see if two variables are independent or not. Just remember here before I close off this chapter, I want you to remember over here that in order for your chi-square results to be meaningful, you must make sure over here that all your EIs or EIJs, if you're going to use the test for independence, you must make sure that they are at least of a value of 5 or more. If not, then you have to apply some remedial measures. The first one being the more restrictive one, whereby you merge some adjacent intervals, um, and so you ensure that your new EIs or EIJs are greater than or equal to 5. Or you can apply the more relaxed set of conditions over here. So here we've got 3 conditions, in which case you can continue to apply the chi-square test. So I hope this has been helpful. I encourage you to go through this document, which is posted in the Done in Class folder, and where I give other examples. And yeah, so that's pretty much it for chapter 12. Okay.